preparing for a quantum research engineer interview. You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you explain the difference between gate model quantum computing and quantum annealing? Gate model quantum computing applies explicit unitary gates to qubits, similar to a programmable circuit. Quantum annealing encodes an optimization problem into an energy landscape and slowly evolves toward a low-energy solution. I compare them by controllability, problem class, and error behavior. Gate models are broader for algorithms like phase estimation or VQE, while annealers target Ising-style optimization. The trade-off is generality versus specialized hardware maturity and embedding constraints. While answering, focus on computational model, problem classes, hardware implications, controllability, optimization use cases, and why gate-based systems are considered more general but often harder to scale fault-tolerantly. Question 2. What are T1 and T2 times, and why do they matter when evaluating qubit quality? Decoherence is the loss of quantum information to the environment. T1 captures energy relaxation, while T2 captures phase coherence loss and includes dephasing. In practice, I connect these times to gate duration, measurement fidelity, and algorithm depth. A qubit with long T1 but poor T2 may still fail phase-sensitive circuits. Research decisions should optimize the full error budget, not a single headline coherence metric alone. Make sure to cover relaxation, dephasing, coherence windows, gate time comparison, measurement fidelity, and why a single coherence metric is insufficient for judging real algorithmic performance. Question 3. Can you explain the idea behind quantum error correction and why the surface code is widely studied? Quantum error correction protects logical information by distributing it across many noisy physical qubits. A surface code is attractive because it uses local stabilizer checks on status and has a high threshold. I would explain syndrome extraction, repeated measurements, decoding, and logical error rates. The key is that correction works only below threshold, and overhead grows quickly as target fidelity tightens substantially in practice. In your answer, talk about logical versus physical qubits, stabilizer measurements, syndrome extraction, thresholds, decoding, locality, and the large overhead required for practical fault-tolerant computation. Question 4. How would you design a VQE experiment for estimating the ground state energy of a small molecule? VQE is a hybrid algorithm for estimating ground state energies when exact diagonalization is too expensive. I would choose a Hamiltonian mapping, pick an ansatz motivated by chemistry or hardware, measure Pauli terms, and use a classical optimizer. Validation means checking small instances against classical solvers, tracking shot noise, and analyzing convergence. I would not claim success without uncertainty bars and sensitivity tests for ansatz and optimizer choices. Be sure to mention Hamiltonian mapping, ansatz selection, Pauli measurement grouping, classical optimizer choice, shot noise, validation against exact methods, and reporting uncertainty rather than only final energy. Question 5. What are barren plateaus in variational quantum algorithms, and how would you mitigate them? Barren plateaus are regions where gradients vanish exponentially, making variational training look random. I watch for flat cost curves, high gradient variance, and optimizer stagnation. Mitigation starts with problem-inspired ansatzes, shallow circuits, local cost functions, careful initialization, and layer-wise training. Hardware noise can mimic the same effect, so I separate algorithmic trainability from noise by running noiseless simulation and controlled noise sweeps before changing architectures. While answering, cover vanishing gradients, circuit depth, random ansatze, global cost functions, initialization strategies, layer-wise training, local costs, noise effects, and separating trainability issues from hardware limitations. Question 6. Why is quantum phase estimation important, and what makes it challenging on near-term hardware? Phase estimation estimates eigenvalues of a unitary using controlled powers, inverse QFT, and measurement. It matters because many quantum speedups reduce a scientific question to learning phases accurately. In chemistry, it can estimate molecular energies given a good state preparation. The interview trade-off is precision versus circuit. Make sure to cover eigenvalue estimation, controlled unitaries, inverse QFT, precision scaling, state preparation, use in chemistry and factoring, and the circuit depth challenge for NISQ devices. Question 7. How would you benchmark the performance of a quantum processor beyond just quoting qubit count? I would not benchmark a quantum processor with one number. I would combine T1, T2, single and 2 qubit fidelities, readout error, connectivity, crosstalk, and drift. Randomized benchmarking estimates average gate error. Interleaved RB isolates a gate, and cycle benchmarking captures layered behavior. For application relevance, I would also run circuit-level benchmarks matching the target workload, because calibration metrics can overstate algorithmic performance on real devices significantly. In your answer, discuss gate fidelities, readout error, coherence, connectivity, crosstalk, drift, randomized benchmarking, application-level benchmarks, and why qubit count alone can be misleading. Question 8. How can you verify that 2 or more qubits are genuinely entangled in an experiment? Entanglement is a non-classical correlation that cannot be written as independent local states. To verify it, I choose the method based on scale. For 2 qubits, Bell state tomography or CHSH violation is clear. For larger systems, I prefer entanglement witnesses, parity oscillations, or randomized measurements. The important caveat is span error. State preparation and measurement mistakes can fake or hide entanglement unless carefully calibrated and bounded. Be sure to mention Bell states, tomography, CHSH tests, entanglement witnesses, parity oscillations, randomized measurements, scalability limits, and the role of span errors in interpretation. Question 9. What approaches would you use to classically simulate quantum circuits, and where do they break down? Classical simulation becomes hard because an n-qubit state has 2 to the power n complex amplitudes. I pick the simulator by circuit structure. State vector simulation is straightforward for moderate qubit counts. Stabilizer simulation is efficient for Clifford circuits. Tensor networks exploit low entanglement or favorable topology. For noisy circuits, density matrices explode faster, so trajectories or approximate methods are often better. I always report limits honestly with scaling estimates. While answering, compare state vector simulation, density matrices, stabilizer methods, tensor networks, sampling, noise simulation, memory scaling, circuit depth, entanglement growth, and when approximations are acceptable. Question 10. What is the difference between quantum error mitigation and quantum error correction? Error mitigation tries to improve expectation values without encoding logical qubits. I would mention zero noise extrapolation, probabilistic error cancellation, readout mitigation, and symmetry verification. These methods can reduce bias, but increase sampling cost and may rely on accurate noise assumptions. Error correction is different. It actively detects syndromes and protects logical information, but needs many physical qubits. Mitigation is useful now, correction is the scalable path. Make sure to cover near-term mitigation methods, logical encoding, syndrome measurements, sampling overhead, assumptions about noise, scalability, and why mitigation cannot fully replace fault tolerance. Question 11. How would you apply QAOA to a combinatorial optimization problem like MaxCut? QAOA maps a combinatorial problem to alternating cost and mixer unitaries. For MaxCut, I encode edges in a cost Hamiltonian, initialize plus states, apply p layers, then optimize angles classically. A strong answer covers parameter transfer, constraints, shot noise, and hardware connectivity. I would benchmark against classical heuristics, not just exact solvers, because practical optimization cares about solution quality per unit time and cost too. In your answer, discuss cost Hamiltonian construction, mixer Hamiltonian, circuit depth P, parameter optimization, constraints, hardware connectivity, classical baselines, approximation quality, and shot-based objective estimation. Question 12. When reading a new quantum computing research paper, How do you evaluate whether the result is credible? When evaluating a quantum paper, I first identify the claimed contribution, algorithm proof, experiment, or engineering improvement. Then I check assumptions, baselines, scaling, noise model, and reproducibility. For experiments, I look for calibration data, uncertainty estimates, and raw enough results to reanalyze. For algorithms, I ask whether the speedup includes state preparation, oracle cost, and readout. Good research survives adversarial baselines and transparent replication attempts well. Be sure to mention checking assumptions, baselines, reproducibility, scaling claims, noise models, statistical significance, code or data availability, hidden costs, and whether classical competitors are fairly represented. Question 13. What does pulse level control mean, and why is it important for quantum hardware research? Pulse level control is where hardware physics meets gates. A calibrated X gate is not magic. It is a shaped microwave or laser pulse tuned for amplitude, phase, frequency, and duration. I would discuss Rabi experiments, Ramsey fringes, dragged pulses, crosstalk, leakage, and drift. The goal is maximizing process fidelity while keeping gates short enough to beat decoherence and stable enough for scheduled circuits in production. While answering, focus on how physical pulses implement gates, calibration experiments, Rabi and Ramsey measurements, leakage, crosstalk, drag shaping, drift, and the connection between control and fidelity. Question 14. How would you assess a claim of quantum advantage or quantum utility? I separate quantum advantage from quantum utility. Advantage means outperforming the best classical method on a defined task. Utility means producing value, even without asymptotic dominance. To evaluate a claim, I check task relevance, classical baselines, data loading, error bars, total runtime, energy cost, and reproducibility. Sampling tasks may show separation but limited usefulness. For research, I want precise claims that survive improved classical algorithms. Make sure to cover definitions, best-known classical baselines, task relevance, runtime accounting, data loading, statistical confidence, reproducibility, hardware assumptions, and the difference between theoretical separation and useful value. Question 15. How would you implement and validate a quantum algorithm using a framework like Qiskit or Cirq? I start with the physics or math specification, not the SDK. Then I translate it into circuits, define qubit ordering, parameter conventions, measurement groups, and expected invariance. In Qiskit or Cirq, I write small deterministic tests, known states, conserved symmetries, and comparison with NumPy for tiny instances. After transpilation, I inspect depth, native gates, connectivity, and noise sensitivity. Correctness before device execution saves expensive debugging. In your answer, mention starting from mathematical specification, circuit construction, qubit ordering, parameter conventions, simulator tests, small classical comparisons, transpilation effects, native gates, noise models, and reproducibility. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.